Next up in buildings and cities is smart glass. Obviously, this is trying to be very comprehensive, so to reaching to all solutions which have a role to play in drawdown of carbon, right? This is ranked by 2050 at number 61 with 2.19 gigatons of reduction in CO2 by then. The net cost is kind of could be a barrier upfront at 932.3 billion dollars, but then the net savings is at 325.1 billion dollars, and we'll see that the lifetime savings could be even larger. Here is something. I will show another figure like this at the end from the book itself. This I took from this site, which is showing a room as a schematic. Here it is summer without any user inside. This is summer with the user. This is winter without user and winter with user, and you can see these beams of light being directed differently. What is it doing? If no user is present in summer, all mirrors switch vertically, keeping the solar heat outside. This saves huge energy by minimizing heat transfer. In B, once user presence is detected by sensors in summer, upper mirrors open and reflect daylight to the ceiling area, so the daylight is directed appropriately. The room stays cool where no user is standing, saving energy on climatization, so AC usage is optimized. Parts of the room far away from the window can be efficiently illuminated by daylight, saving energy on artificial light, so you can also optimize internal lighting requirements. If no user is present in winter, all mirrors open and harvest energy by reflecting solar radiation onto a wall, acting as a radiation heater. This saves energy on heating, of course. Once user presence is detected in winter, all the mirrors will redirect complete solar radiation to the ceiling to minimize glare. So the angle at high latitudes where you have strong seasonality can result in glare, angle of the sun. Now the ceiling acts as a radiation heater, saving heating energy. So obviously there is a concept of the Internet of Things which has sensors to detect real-time weather, internal user movements, lighting requirements, heating requirements, so monitoring temperature, etc. Is going to be perfect for optimizing human comfort, work productivity, as well as energy use. So this is an example of these smart glasses basically can be electrochromic, where electricity determines the change in the color that will allow heat and light through the glass. Photochromic, where light detects the need for darkening or clearing up the glass, like photochromic glasses I wear. When I go outside in the sun, it obviously becomes darker, as I will show in a minute. And electrochromic, photochromic, and thermochromic, so temperature dependent changes in the glass properties as well. All are done by coating certain oxides which react either to electricity or light or temperature. So this is from NREL, electrochromic glass changing color under electric control. So it looks like normal glass here, but once you run electricity through it, you see that it becomes opaque, bluish or dark. This is photochromic lenses from Lenscard that I just took from the web. You can choose gray and brown. I think mine are gray in the sun. So outdoor, when there is normal indoor light level, the glasses remain normal, and when you are bright outdoor, it gets darker with the chosen shade, and then when it's you're outdoor and it's normal, like maybe nighttime and no sunlight, it also remains normal. Very simple idea. The Boeing Dreamliner, for example, has given now the passengers a control on how they want to shade the window instead of just pulling shut or open with transparent glasses. Now you can control the shade level depending on whether you want to sleep or work or watch a movie on the screen in front of you, and so on and so forth. Okay, so smart glass is an up-and-coming solution with a current adoption in only 0.004% of commercial building space. We assume that growth will occur primarily in the commercial sector in high-income countries and can reach 29% of the new commercial building space by 2050. The potential energy efficiency from cooling is estimated at 23% and lighting at 35%. Both will vary depending on local climate and building location. Adopting smart glass can result in 2.2 gigatons of emissions reductions from decreased energy use. The financial cost is high at $932 billion, yielding a 30-year operational saving of $325 billion, but a lifetime saving of $3.6 trillion. Okay, let's look at another example here from the book now, showing a building at 9 a.m., 12 p.m., 6 p.m. and 9 p.m. You can see the different lighting depending on where the sun is shining and what time of the day it is and what the heating, cooling and light requirements are indoors. So electrochromic glass responds to 4 different times of the day from 2 facings of a building. When tinted, the glass is reducing solar radiation and workplace glare as well as the air conditioning load while maintaining daylight illumination inside. Sensors and even real-time weather data will override settings for daytime and allow more incoming light. The building is programmed by algorithms to respond to seasonal shifts in temperature and light. However, single panes of glass can be controlled from a smartphone at the user's desk to adjust glare, light and tint. So this is again getting closer to that Internet of Things where instrumentation controls the operation of the smart glass and the light, glare and tint and so on inside for optimal work conditions. Okay, so obviously high cost but long-term investment for long-term savings, a no regret solution.